Let me start recording. So this is Aerial Robotics, second part of the lecture of Bitcraze. Kimberly still there. And so the floor is yours again. Thanks. You have to unmute yourself, Kimberly. We couldn't hear you so far.
Thank you. Sorry, you guys. I still have to get used to Zoom. All right. Happy to see you guys all back virtually. Let's start with the second part of the lecture. Let me share my desktop. All right. Share. All right, so just a quick recap what we've discussed about last lecture. So the Crazyflie, obviously, the CF client and how you're able to log, see some variables in the plotting tab, and also the console tab, which is going to be very handy for you guys. And the Flowdeck, just some hardware specifics. I'm going to go a bit more into detail this hour as well, more on the software side, because well, you guys already seen this, so I can skip this. So yeah, what do you need to fly? Well, of course, hardware, last hour. And now we're going to go into software, or more specifically also called firmware, because it's also a microprocessor. I'm going to really talk about all the important elements that are in the actual Crazyflie firmware. So here is a grand overview of all the software modules or firmware modules in the Crazyflie. So obviously you need to read out the sensors, very important, and need to be able to distribute your power to your motors. And this is all pretty much where all the magic happens. So you need an estimator to estimate your state. You need controllers to be able to do something with that state, and you need a commander to set points. And that is, if you look here from the communication part, and this is pretty much when you communicate with your actual computer. So you have logs, but you also have parameters. So you're able to set parameters in the CF client as well. You're able to load trajectories to memory. So I don't know if you guys remember the actual demo that I did this morning. That was a trajectory that was fully on board. So that's everything that you can also do with that as well. And you need to have drivers to read out the sensor of the decks. So every time you put on a new deck, a driver will be initialized to be able to handle that deck. To also answer the question that one of you guys had last hour as well. So I can pretty much already spend a few hours explaining all of this, but we have limited time. So I'm just going to mostly discuss this part, which are the common estimators, the controllers, and the commander. So first, a very quick overview of that. Very important to have like sensors, so that's most likely IMU, but also all the sensors that you get if you add an expansion deck on the Crazyflie. So if you add a Flowdeck, then suddenly you have a motion sensor and a ranging sensor as well. If you put on the lighthouse system, then you have input of these HEC5 base station that you need to do something with. And that the something that you do with that is you send that to a state estimator that uses those sensor inputs to get out like position, velocity, also the angles, because gyroscopes, like I said before, are not measuring absolute angle, they are measuring the speed that the angles are going. So those have to be estimated as well. Once you have a nice state estimated, then you send that to a controller. And that controller, of course, needs a desired state that it wants the Crazyflie to be in. So that's what the commander is doing. So it sends out the set point to the state controller. It compares that with the estimated state, and it sends out commands, which is send out to the power distribution, which distributed to the motors, and then finally that will affect what the sensor will read, because the Crazyflie will fly, and then the sensors will be disturbed in a certain way. So this is a very rough overview. I will go into each of these blocks as the lecture progresses, but at least if you want to know where you can find this in the actual firmware, I try to also show the location in the actual firmware. So you guys can look back at it and actually look how it's actually been implemented. So first, state estimators. So state estimation, very important. I will already assume that you guys already know what a state estimator is, I presume. So we have two main state estimators in the Crazyflie. First is something that we call a complementary filter, which is a very low weight, efficient filter that just uses the gyroscopes and accelerometers. And also, if you have a Z-Ranger deck, which is the Flowdeck without the optical flow sensor, to get altitude and attitude. So attitude is, of course, the roll, pitch, and yaw. Attitude is the height on which it's flying with. So we like to use this filter mostly when we're flying manually because it's very quick, it's very efficient, there's no fuss, no buzz. And actually there's a lot of people that actually say that the attitude estimation on this filter is much better. But since you guys are going to use the Flowdeck, this is going to be the one that you're going to be most interested in, which is the extended Kalman filter. So this pretty much has the sensors of all the Flowdeck. So the internal sensors like the gyroscope, accelerometers. If you put on a Flowdeck, flow and the range sensors, the LPS deck, the ultra wideband module, then you get the distances. Lighthouse deck, you get the sweep angles of these base stations right here. And yeah, if you also have motion capture, then you just get the full pose. So these are all possibilities of what you can put into the extended Kalman filter in order to get the state out, which is in this case attitude, position, and velocity. So of course we're going to mostly focus on this one. How the Flowdeck sensor data is transformed into the state estimation. So just some details. I'm not going to go into the extended Kalman filter because, as I've already said before, this is already something that you guys already had in the lecture, so you should know what it is. But just going to give you some data so you can have some background information when you want to read up. So it's originally implemented by ETA Zurich. So you have the references right here if you want to read up. It's quite interesting read. Definitely would recommend it. And then of course they use the quadrotor motion model. And initially they used the ultra wideband LPS system to implement it, if I remember correctly. So they actually have a measurement model of the LPS system, which pretty much transform distances, because that's all that the Crazyflie gets. It gets the distance from a tag to its actual position. And then from the distances it gets from multiple tags, it's able to infer its own position. So that's what that measurement model will actually convey. The Lighthouse system is a bit different because what they actually, what the Crazyflie will receive is a sweep angle, like the angle on which part of the Crazyflie is being detected. So it has an angle from this part, from the X and Y axis, and also from the other base station, and from that is able to get its own position. So that's very rough set how the Lighthouse measurement model is being conveyed. The Flowdeck is of course very important because that is what you guys are going to talk about. So I'm going to go into how the measurement model of that one is built up. Right, so you have here a nice equation. It shouldn't look too difficult, but let me explain what each of the elements are. So this is of course velocity, to be particular in the X direction. So what you want to do is to calculate the velocity by using the optical flow sensor and the height sensor. Of course you need a bit more data than that, but that is kind of the major goal of this formula. And that is where the measurement model is based on. So this is the height, obviously, that you get from the optical flow sensor. And then you'll also get the flow, which is just like the pixels within a certain sample time. So the accumulated pixel measured, movement measured in a sample time. But you also need some extra data because you need to, for instance, know how big the sensor is, how many pixels the sensor actually has. Well, it has 30 pixels. Now you guys know. You can also find it back in the firmware. On the last slide, I put also the location of the firmware files if you want to look and see for yourself. And then the field of view, very small field of view, only 4.2 degrees. But that are information that you need to at least get the velocity out. But that's not where it ends. Because what will happen if you have a Crazyflie and you actually move it like this? Then it is at the same position, it's not moving anywhere, but you're still seeing flow. So if you actually have that in your state estimator and your Crazyflie is moving like this, it's of course moving at an angle if it moves in a certain direction. So you need an extra factor, which is you need to subtract it with the gyroscope measurement times the height. So is everything clear about this formula until now? I guess it is probably, but if you want to know more, the reference of the master student who actually implemented this measurement model. He made a thesis and it's actually very clearly explained in his thesis right here, so you can look it up for yourself. I guess I maybe have a question for you guys if you're paying attention still. Do you think there's something missing to this formula? Is there any other factor that needs to be subtracted from this? If you guys are still awake. All right. I hope I'm still online. Can somebody... Oh yeah, thank you for answering. I was a bit afraid that you guys were not receiving me anyway, so it's... All right, so you're asking, Tafat is asking, while not moving, can we also get information on the rotation from the optical flow? Can we also get information on the rotation from the optical flow? Yes, you can. So like if you're assuming that you're not moving and you see a rotation, you know what the height is, then you can also infer the actual rotation go around. So that in that sense, you can also get, yeah, the attitude in a sense. However, the gyroscope is much faster than the optical flow sensor. So I would most likely just use that because that is information that you already have to subtract that factor from the velocity estimation from the Flowdeck. So yeah, so, but is that clear to you? Yes, great. So about my other question or little pop quiz question, I guess nobody really, do we have to, oh, okay. Do we have to subtract an angular speed factor? Do you mean the gyroscope measurement? Because that's the angular speed factor, I would say. Because that is this part right here. But I guess the pop quiz question is not necessarily, it's right now I'm talking about the angles in roll and pitch. But if you do a yaw, what will happen? Well, you will get flow in here. But a very important thing for you guys to know is that currently in our measurement model on the Crazyflie, we do not take into account when the Crazyflie is rotating in his yaw, it's not subtracting that optical flow. So just for you, for the future, if you work with the Crazyflie and let it rotate very quickly, you will definitely see a drift. So just something to keep in mind. So any other questions about this before I move on? Yes, but you can use the exact same formula for y because it's symmetrical. So you have the same pixel width and you have the same field of view. So this is the answer to the question if the formula is for optical flow only around the x. It is, yes. All right, is that great? Why not subtracting it? Isaac, are you referring to the rotation around yaw? Yeah, good question. So the person that implemented this, he assumes that the angle will be so small that it's not going to be that much effect. But I actually found out during my research, the Crazyflie that I was using during my research was actually yawing quite a bit. So I would have liked to see it subtracted, yes. But it's also a bit difficult to estimate. It's like roll is pretty easy to estimate because you just have to multiply it by the height. But yaw, that's like the flow is quicker around the sides of it than in the middle. So that's, you know, a bit more difficult to estimate how that's going to be. But if you guys manage to get your hands on the Crazyflie, go ahead and test it out. And let us know. We're very curious. All right, let me continue. I hope everything is correct. So just ask me questions at the end of this lecture if you're still unclear about something. All right, okay, so let me just go to the client again. Oop. So, right. So I still have the flights. Let's see. Connect. One moment. Yes, all right, it's connected. And okay, let's see what the state estimator is going to do. So we're going to logging settings, logging configurations, and select, okay, position. So what does the position do? So then we try to find the state. So state estimates. So we'll just look at the position state estimates for now. All right, just save position. All right, let me just go back to auto so you can actually see everything. So you can see, I think this is in millimeters though, but you can see if I put the Crazyflie up and down, that the Z-axis will actually give a position. You're all seeing that, right? Yeah. Now I'm moving the Crazyflie forward and backwards. All right, yeah, that's a pretty good estimate. Okay, now sideways. So that is actually the position estimate. That is what the controller will use eventually for, controlling actually. It's all entire Crazyflie. All right, so what will happen? I have a table right here, if you can see. What will happen if I move the Crazyflie over the table? Oops, it suddenly thinks it's higher. All right, there is a question. Can you do circles? Let's say if you, with the Flowdeck? Do you mean that, Dario? Yes, you can. So you can give it a command to rotate. You just have to do it slowly. If you do it too fast, it will drift. If you can fly like a circle. That is actually what I would say, that if you want your Crazyflie to move, always do that as a circle, because then it also gets some forward flow as well. I did it also during my research. That worked much better than having the Crazyflie just fly at a certain position and rotate. Dario, does that answer your question? Thanks. All right, so that is, so when I was moving away from the table, suddenly it thinks it's higher, which is Not exactly accurate, but dependable because it's doing that based on the height sensor it has on the bottom. So that is completely logical that it will do. So before, in the last lecture, I actually said that the Crazyflie has a barometer. Let's see if we're able to also maybe make a nice looking configuration for that baro. Let's see if we can find the barometer. That would be nice. Pressure. All right. Save. Let's go to the barometer. Because, of course, if you can see, you're still not seeing anything. That's interesting. Oh, wait, sorry. I didn't prepare this, but the barometer is by standard off in the Crazyflie. So I would actually need to change the firmware. But you can use the barometer in the state estimator. So that's maybe something for you guys to try out, because if you would use the barometer and you would change your position, no matter what there's underneath there, the pressure will stay the same. It's just a lot more noisier than the height measurement. So that's just something to be worried about. But there's all kinds of things that you can try out and play with. All right, let's. I can also quickly show you how the estimator will look like. State estimation will look like if you actually replace the Flowdeck with a lighthouse deck. Let's see if we can connect to it. And then we go back to position. So you can also see the height changing. The zero position is actually somewhere more here. But you can of course see, because it's not determining his state estimation on the Flowdeck, it doesn't really matter if I'm flying over the table or not. It's just staying at, the state estimation just staying at the same height. All right, so I think this is pretty clear for you guys. So I'll move on with the lecture. I have some more flying coming up, so I promise. We'll still have some nice demos to show. Okay. So, okay, so we've covered, since the last lecture, we covered the state estimator and how you're able to read it out from the console, and also how the Flowdeck is actually estimating velocity. Now we're going to the controllers. That is right here. So you have different levels of control. So you have position velocity, that's pretty much like one of the highest controllers that we have. Well, above actually you have like trajectory control, but let's say that this is the highest. Then you have attitude control and attitude rate control. Attitude rate is just pretty much gyroscope, raw gyroscopes all the way, but I'll explain it later. But we also have actually 3 types of controllers in the Crazyflie. First is the good old PID, which is actually being done on all 3 levels, in separate one. Then we also have a fancy one, which is all fresh new. It's called the incremental nonlinear dynamic inversion controller. I'm not going to explain it here, that will already take me another hour, but I have the references right here in the lecture, so you can also check it out if you want to. And it's also very new, so we haven't really tried it out to the fullest. And we actually, now you see here PID, but as of recent, we actually got a pull request for a position velocity controller, also an INDI. So I'm going to be excited to try that one out. But it's very new, so I would, for you guys to maybe work on the PD. Oh yeah, and we also have the Mellinger controller, which is quite nice because it does all the velocity, position velocity and attitude rate controller all in one. So this is, we would say, our favorite controller. However, you need millimeter precision. So if you're flying this any other than a motion capture system or the lighthouse system, you're going to have a bad time. It's going to be a way too aggressive controller. It's still really cool though, but since you guys are using the Flowdeck, we're mostly going to focus on the PID controller. So let's go a bit more deeper into that. So what we have is a cascaded PID controller. I'm assuming that all of you guys know what a PID controller is, but I'm just going to show you how it's implemented into the Crazyflie. So lowest level, an attitude rate PID controller. So it receives the actual raw, well, slightly filtered gyroscope rates, angle rates in as the measurement, and it gets the desired attitude rate from someplace, let's say, and it takes the difference and it does a PID magic, and you output motor commands. Right now it's implemented at 500 Hertz. However, it was supposed to be a bit higher, I think twice as high, because this is sampled at 1000 Hertz. So it's also interesting if we implement this at a higher rate, if that would actually improve the results. But anyway, that is how it's implemented right now, is 500 Hertz. One level higher is the attitude PID. So now actually the sensor measurements, like the gyroscope measurements, are going into the state estimator. And that sends out the estimated attitude, attitude to the attitude PID controller. So, and then you of course have something is saying, okay, I want your yaw to be this, then your yaw is going to be this. This runs at 500 Hertz for sure. And it sends out desired attitude rate for the attitude rate PID controller. But that's not all. We of course have a point of position PID controller. So yeah, it's quite cascaded. It's quite cascaded for sure. The state estimator also gets the sends out the estimated position, which position PID controller takes the difference between the desired position and the estimated position to output desired attitude, and that runs at 100 Hertz. You don't necessarily only have to do position, you can also do velocity, that's all fine. So, any questions about this thing so far? I don't think so. Okay, still everything clear. Either I'm explaining everything right, or everybody's sleeping by now. Well, if you're sleeping, don't sleep, because I'm going to show something flying again, so better wake up. Okay, so I'm going to give this nice Crazyflie a battery. Okay, make sure that everything is tight. Alrighty. Okay, and now I'm going to stop sharing my screen, and I'm going to share this because I'm going to let it fly again. All right. So I have a question about if the PID controller is required for the rule of thumb. It is not. I think it can be much faster, but in terms of performance, it might not make that much of a difference. You also want to leave some processing capabilities for other stuff as well. So back to the demo. Let's see if you guys are seeing this correctly. One moment, let me just make it fly a bit closer so you guys can really see it actually flying here. Let's see if it does what I want to do. Of course it doesn't. It's right now flying with the lighthouse system again, by the way. Yeah, that's much better. That's much closer, right? You can all see it? All right, let me just switch. So I made a nice script over the weekend. So I hope you guys are going to be also a bit excited about it as I am. So let me just give you a quick share of how it looks like. It looks like this. So this is quite nice. And I can actually give it gains, tune it, do a step response, and also change like the axis that I want to tune my controller with. And this is just only for the PID controller. Let's see. I will just go back to the camera, and I will actually give it a step response. So it just goes a bit up and then goes down again. And then I'm just going to tune the P gain a bit, send it, and do another step response. A bit of an overshoot there. All right, let me share the screen again of the scripts. So you guys see the first one, that's a bit transparent, and with the higher D gain, of course, it's, or P gain, I mean, it is of course a bit overshooting. So if I send an even higher one and do a step response, it's definitely not liking that at all. It's right now only for position PIDs, but I'm definitely very motivated of getting it to work for attitude PID parameters. But this is like very new script. So, all right. So you guys see the gain limits to keep stability. Ooh, yeah, good question. This is on your own risk for sure. Like for instance, let me first add a D gain because I put a very high proportional gain on it. So I will now add a little bit of a D gain now, and I'll send it. And then you can see that it's a bit damped. So I would say, just like roughly speaking, if I just now remove the D gain now a little bit, and if I would, for instance, put it to the P gain to 8, that is going to be a bit more difficult. Let's see what happens. Yeah, it's not unstable, but it's getting close. So if you want to know what the instability is, you can try it out for yourself. But I want to kind of keep this Crazyflie flying because I like this Crazyflie and I don't want it to die. But it's, I would say that higher than 8 for all directions. I definitely would not go any higher than that for the P gain. And of course, the I gain, the integral gain, and the differential gain all has to be lower than that. So pretty much how you would tune your own PD controller. But at least this script will make it easier for you. Does this kind of answer your question? Ella? Ellie? Yes. Risk taking, yes. I'm taking a huge risk here. It's fine. It's, let's see, there is also, why is there a 0.2 second before the C position start racing? Very good question. So this script didn't exist before I started working on it. I'm just saying that the attitude controller and the attitude rate controller are not tuned properly. So those are still too small. So even though I tune it out a bit, I would say like a P gain of 4 and a D gain of 1 was already pretty good, I would say. So that was already quite quick. And if I would have put it back, all those gains, then you go to the old one, which is pretty slow. So I would say that, yeah, attitude and the attitude rate controller, that's why I'm motivated to also make scripts for those are not tuned properly yet. All right. So this is the Crazyflie still flying here. I still have enough battery left, so that's still perfectly fine. I can also change like to the Y axis as well. That is very under-tuned. But if I add it a little bit of P gain and do that, all right. Yeah, that's already close to it. But anyway, it's a nice script for you guys to try out. I put in also the link where you can find it in the in the presentation. You're also able to do this with the Flowdeck, but I must say on your own risk. So don't change the gains as quickly as possible. Yes, they are on GitHub now, actually, yeah. Don't change the gains like it's crazy, and don't start destroying your Crazyflie like I do. With the Flowdeck, it might you just need to make some incremental changes, I would say. Average flight time is 6 minutes, by the way, with this battery. But I had some better batteries during my research, so I have like about 9 minutes of flight time then, and that was with expansion deck. So, but with this battery is about 6 minutes. Oh, see? It has a red, light, so I have to change the battery. Let's make it stop. All right. Cool. Okay, so let me just share my desktop again and go back to the presentation. How are we doing on time? Well, perfect. And I hope everything is still clear to you guys, but it seems that you guys have woken up because of the flight. All right. So last thing I'm going to talk about, I'm not going to go as much into detail as with the other ones, but this is the commander. The commander, what we call the commander is pretty much the one that sets the set points for the controller, who says which set point or which desired state they want the Crazyflie to be. That's what we call a commander. And you can have an attitude commander. So for instance, if you would want to fly it with a controller and you just want to set it to a certain attitude, that's the attitude commander. So you just send the desired attitudes right here. Position of velocity commander, that's like, okay, I want it to fly with 0.3 meters per second, or I want it to go to XY 1, 2 or something like that. So that's the position velocity controller. And this is the velocity controller is what I used during my research for the science robotics paper. You can also have the high level commander, which is, it's not really necessarily a controller, it's more of a trajectory planner. So if you guys were paying attention earlier with the whole firmware setup, it is possible to upload an entire trajectory on board the Crazyflie. And so the trajectory planner, the high level commander, is just kind of controlling that trajectory and just sending position set points constantly to the Crazyflie. So that is pretty much what it's doing. So yeah, that is not much explained necessary here. It's pretty self-explanatory. But I can show you an example of the high-level commander of this research done by the University of Southern California. So this is actually about 40. Crazyflies were about 30, I think. I didn't have time to count because they are they already had preloaded trajectories onto the inside of their memory. So they also just executed all at the same time. But that is quite handy, mostly if you want to make sure that all of them can fly at the same time, because it's actually quite difficult to communicate with all 30, 40 of them at the same time and say like, okay, it's time 1, you need to be here, and you need to be here, and you need to be here. So on-board, off-board trajectory control with 30 or 40 of these is going to be very difficult. So it's very handy to already have a high-level commander on board the Crazyflie with the trajectories. It's just one more time. But it's, yeah, some really nice work by one of our community members. So I don't know if you guys see in our website, but the light photo of our main website is pretty much this in the dark. So yeah, all right. Okay, so I'm going to go through a quick script with you guys. So the what I'm going to show you is a flight with the Flowdeck itself. So I'm going to show you guys this script very quickly, just going to go through the Python script. Oh, wait, I have one more question. Let me just answer that for now. Fabrizio is asking, with how many Crazyflies can you communicate reliably with one radio up to your experience? Good question. Would say with our current firmware, we would say 3 or 4. However, our demos, when we fly with 9 of them, we managed to do that with one Crazy radio. The thing is how much you want to communicate with that crazy radio. Because if you want to communicate a lot, 3 for sure. If you just want to give it like a sign of okay, start your sequence now, or start taking off now and let the Crazyflie do everything by itself and only give it some commands every once in a while, then then you don't need to communicate with it that much. And then you can pretty much have 9 per crazy radio. There's also a ROS package for people that like the robotic operating system. There's a ROS package that actually optimized the communication with the Crazyflies by the max. So they were for sure able to get like 9 Crazyflies per crazy radio. So it depends on how much you want to communicate to them. Yeah. All right. So where was I? Oh yeah, I was here to show you guys the scripts. So just like regular Python libraries, very important, the URI, as we discussed about. So like if you have something different, it won't be able to detect it. And this is the main, so that's pretty much where you start up your script. And these are a couple of things that are just necessary. Here's where you actually connect with the Crazyflie. So here's where you actually take the URI and you connect to the Crazyflie and you sync up with it. The motion commander is what we usually use with the Flowdeck. So that's kind of saying it's the position commander, I would say. Yeah. So the motion commander indeed. And the Multiranger is pretty much a logging, setting up logging for the range sensors. Because the Multiranger, you guys haven't seen it yet, but I will show you very quickly. So that is what I'm going to use to show this demo. So pretty much while you're flying, if you start the script up, the Crazyflie will already start flying at a certain height. I now put it at 0.8 meters. But usually it's like 0.3. If you're a bit careful, you still want to figure it out, just make it fly low, but not too low. 0.3 is just fine. But if you make it fly at 0.1 height, you will have something called like downwash effect with the ground. That is not going to be good for Crazyflie's performance. So pretty much here, it's just like if something is close to the front of the Multiranger or the back, it will just add a velocity command to something else, to the actual command. So it will actually move away from you. And yeah, if I put the handle on top of the Crazyflie, it will stop the script. So yeah, this is a pretty simple script, but you can kind of use it as a base if you want to go and write your own application for sure. All right, so let me just stop sharing this and show you how I'm going to transform this now into the Multiranger one. So this is the exact same setup that I used during my research, where I pretty much only used the Multiranger and the Flowdeck for the initial experiments. And that's pretty much all you need for autonomous identification. Did show one with where I added the camera, but that wasn't actually used for the navigation itself. All right. So you have the Multiranger right here. There are symbols on there so you can see if it's on the right, mounted in the right direction. Definitely important for the Flowdeck. This one is the Flowdeck right here. So you now have 2 expansion decks on this Crazyflie. Oh yeah, have to change the battery, of course, because that was very low. So let me do that first. So also remember, when you're flying and you're using the batteries, do not let your batteries deplete completely. That will really make the battery is terrible for the quality of the battery. So don't do that. If you see a red, the red LED go on, just turn the Crazyflie off and charge the battery. Just a big tip for you guys. All right, so let's put it on the floor. And I will follow it with my Crazy Cam. So that is. I will follow it so you guys can see it a bit more easier. Let's see. Oh. Oh, whoops. It was actually losing connection. It is actually affected a bit by the light, so let me see if you guys can. One moment. All right, can you guys all see it clearly on the crazy cam? Yes, perfect. Okay. So apparently also the products a bit affected by sunlight, so that's also maybe something to be aware of. But now it's just flying by itself without the lighthouse deck, with only the Flowdeck. And how you can actually start noticing that is if you put your hand underneath. Let's just go crazy. Let's do it. Oh, yeah. So you know the state estimator is actually assuming that the height is the laser range sensor, which is relative positioning, as I said before. All right, so if I push a little bit to that direction, or that direction, all right, it's a bit slow, but it also, if you put this whole thing on board, right now it's communicating with the computer and back, so there's always a little bit of a delay, but if you put this application on board, which we have, then this reaction is also much quicker. All right. So this is hopefully it's going to be something that you can also try out. There's also other scripts in the GitHub repository that you can also try out. That only uses the Flowdeck. So you don't necessarily have to have the Multiranger in order to already do something cool. And just see if we see any questions. Right. Okay, cool. Let me just land it. All right, now it was flying at 0.8 meters. All right. Do you guys want to see that again, or were you able to? Okay, I guess everybody was already able to see it. Just look at the time. It's actually quite close already to close. So that was actually the last slide that I have. Let me just quickly share the last one that I have. So this is just the general contact information if you want to know anything more about, oh wait, let me just first share. Yes. If you want to share more comments or questions, or if you want some help. So we have a nice website where we have tutorials how to work with it. If you are able to finally fly with your Crazyflies. If you have any problems, either get help with your, like the one that your supervisor says that should be able to help you, or post something and post on the forum. Unfortunately, if you guys put your entire project description in the forum, I will definitely see if it's a project description. There are things that you have to do yourself. It is still an assignment. But I hope it's going to be fun for you guys to at least work with the Crazyflie. And yeah, just also if you need to email us, you have any questions about specific things about the Crazyflie or need some more information, go ahead and send us an email or use the forum. So that was pretty much my lecture. I think was able to explain everything that I needed to explain. Unfortunately, I wasn't able to go into too much detail on some of the things, but I can pretty much, yeah, it's there's a lot to this, but I actually hope that this will give you a good startup to start working with the Crazyflie. Thank you, guys.
Thanks a lot, Kimberly. I wanted to thank you personally, and it was a great lecture. I hope that everyone enjoyed, and as Dario said, I hope that we will be able to do the crazy practicals.
Yeah, I hope so too. Yeah, I know it's all going to be very difficult in terms of with the COVID, but you know, as you can see, you can have your flag like right here in the kitchen, so it's there are possibilities. Yeah, but I hope you guys are able to do everything you can. And I'm very happy that I was allowed to be here or virtually be at EPFL to do this lecture.
Yes, next time we will make it in person. Thanks a lot.
Oh yeah, definitely.
All right, good. If you don't have any other questions, I think I will stop recording. Wait like a few seconds.
All right.